So this question on equilibrium, we're told that carbonyl chloride decomposes to carbonyl and chlorine at high temperatures, and we're told that the Kc at 600 Kelvin for the reaction is 0.0071. Alright, and then we're given the equilibrium for the decomposition, and we're told if 0.05 mole of carbonyl chloride is placed in a 12.5 liter flask, what is the total pressure at equilibrium at 600 Kelvin? Right, so to get to the total pressure, there's a couple of ways that you can do that, but one way that we can, the first thing that we can think of is, well, pressure is equal to, well, let's start there, PV is equal to nRT, right? So we want the total pressure, so we want the pressure. We know what the volume of the flask is in which this equilibrium lies, right? It will be the total volume of the flask. We know what R is, and we know the temperature at which this equilibrium is. So there's the pressure is what we're interested in. So the parameter that we need to calculate is this N. And if we rewrite this to say that P total, which is what we're after, is equal to N total RT divided by V total, then we see, well, V total, that's not relevant because, well, it is the total volume, just the volume. Then hopefully it becomes, you can remind yourself of what we actually need to do here, because remember, the total pressure of a mixture of ideal gases, so this is what we're looking at, so we assume these are ideal gases, is equal to the total number of mole, which is the sum of all the individual number of moles. So N total, just going to call it NT for now, is equal to the number of mole of the carbonyl chloride plus the number of mole of the carbon monoxide plus the number of mole of the chlorine. Right, and that multiplied by RT divided by the total volume, or the volume of the flask, gives us the total pressure. So we want to get to what the total number of mole is. And of course, recalling that, well, concentration is equal to number of mole divided by volume, if there's a way that we can get the concentration of these species at equilibrium, then we have a way of determining the number of mole of the species at equilibrium, right? And we know how to do that. We have a way to determine the concentration of these species, and that is through an ice table. So that is our strategy. We want to determine the concentration of these species at equilibrium. So let's start. We're told we place a certain amount of carbonyl chloride at equilibrium, or we place it, and then we allow the system to reach equilibrium. We don't place any of the products in there, so hence we only start with the carbonyl chloride, which is carbonyl chloride 0.050 mole divided by 12.5 liter, right? It's N over V, that gives you concentration, so that's 4.0 times 10 to the power minus 3 molar. All right, and the concentration of our two products initially is equal to 0 molar. Alright, so I just skipped ahead. There's the ice table now. I've just filled in the initial concentrations for us. So our next step is to determine in which direction does the equilibrium proceed, or the initial situation proceed towards equilibrium. And of course, the way that we always do that is by using our reaction quotient. So our reaction quotient is equal to our products, which is in this case CO, Cl2, divided by concentration of carbonyl chloride, and putting in the initial concentrations 0, 0, and divided by 4.0 times 10 to the negative 3, right? Which is of course 0. So that is indeed less than Kc, which is equal to 0.0071, and therefore we are not at equilibrium, right? Because Q is not equal to Kc. Q is in fact less than Kc, so this situation is not serendipitously at equilibrium. And because Q is less than Kc, Q less than Kc, it implies the forward reaction is favored. Right, until equilibrium is reached. Right, so that means we will need to decrease our product concentrations, our reactant concentrations, and increase our product concentrations. There's no stoichiometry to worry about, so everything is 1 to 1 to 1. All right, so that gives us at equilibrium, the concentrations for carbonyl chloride will be 4 times 10 to the negative 3 minus x. For carbon monoxide, it's going to be x, and chlorine gas, it will be x. Then to calculate this x, as always, we use the Kc expression, right? And that is as follows. So we use the value, and we put in these values. So it's going to be x times x divided by 4 times 10 to the negative 3 minus x. So that means we get x squared divided by 4.0 times 10 to the negative 3 minus x. Now let's quickly check if we can do the approximation. So Kc times 100 is equal to 0.71, but 0.71 is still much larger than our initial CoCl2 concentration, right, which is 0.004. So that means we cannot make the approximation. This x here minus x is indeed significant, so we need to carry it throughout our calculation. So let's just continue on with that. So that means if I solve here, I'll start simplifying. The quadratic expression that I got is 2.84 times 10 to the negative 5 minus 0.0071x minus x squared is equal to 0. So relatively okay one, only the numbers need to multiply with each other. The x is multiplied with 0.071 and the x squared just goes across the equal sign. Right, so that means we use the quadratic equation to solve for x. We use minus b plus minus the square root of b squared minus 4ac divided by 2a, right? And everything is the coefficients here. This is c, this is b, and this is a. So a is minus 1, b is minus 0.0071, and c is 2.84 times 10 to the negative 5. And that gives us values for, so the two roots of the quadratic expression. x1 is equal to minus 9.95 and some numbers times 10 to the negative 3 molar. x2 is equal to 2.883 times 10 to the negative 3 molar. Right, this can't be a negative quantity. It can never be a negative quantity, but especially because x must be purely the concentration of some of the species at equilibrium. So this one is impossible. Root 1 is impossible. that means we go with x2. Alright, and then we just plug it in. So therefore our concentrations at equilibrium, so concentration of CoCl2, carbonyl chloride, at equilibrium is equal to 4.0 times 10 to the negative 3 minus x. And well, we don't really ask for them. Yeah, we're not asked for them, so they're not. We don't have to give them rounded really, but I accidentally rounded them here. So 1.1 times 10 to the negative 3 molar. Then concentration of CO at equilibrium is just equal to x, and rounded that gives 2.9 times 10 to the negative 3 molar, and Cl2 at equilibrium is also just equal to x, also rounded 2.9 times 10 to the negative 3 molar. Alright, but because they're technically not asked as final answers, in principle you should not be rounding them. So just quickly want to check what that answer is. 853. So this is this one, let's just make a note of it. It is 1.147 times 10 to the negative 3 molar. Right? And these of course are x, so they're 2.853 and so forth. So you keep all the numbers because we're going to use them now subsequently. Because what we want to do is this whole thing that we explained here at the top. We want to use these concentrations to get the number of mole of each of these. So what we actually want to do is we want to say, right, now we have the concentrations, but what we actually want is we want the number of mole of CoCl2 at equilibrium, and that we can calculate from the concentration of CoCl2 at equilibrium multiplied by the volume. Alright, and remember, concentration, molar, is mole per liter. The volume is already in liters, so we can just say this is purely equal then to the 1.147 times 10 to the negative 3 molar multiplied by 12.5 liter. Right, and the value that I got here, that wasn't rounded, so 0.01433, bunch of numbers, mole. Right, that is what it is. I'm just going to add a page. Alright, so that's the value that I got there. And you do that for the other two as well, but they are going to be equal. So the number of mole of CO at equilibrium is equal to the number of mole of Cl2 at equilibrium, right? Because their concentrations are equal. So that is just equal to whatever their number of, so you can choose whatever, so it's concentration times volume. And the value that I got here is 0.035 mole. Alright. So then from that we must get the total number of mole of the gas. And that is equal to the sum of the carbonyl chloride plus the carbon monoxide plus the chlorine gas. Alright, so it is 0.01433 plus 0.035 plus 0.035. Alright, and that gave me a total value of 0.08566 and some numbers mole gas. Okay, so then finally from that we can calculate the pressure. So the total pressure is equal to the total number of moles divided by, multiplied by RT divided by the volume of the flask. So it's going to be this 0.08566 mole multiplied by 8.3145 joule per Kelvin per mole. And then the temperature is 600 Kelvin, right? Because that's what the equilibrium is at 600 Kelvin. And the volume is 12.5 liter. Now 12.5 liter, we need to remember what we actually need or actually want to work in here. So if you're working in, so if your R value is in joule per Kelvin per mole, and you have everything, well, joule per Kelvin per mole, then you have to work in cubic meter, right? So we have to convert this value to cubic meter. There is 1,000 liter in 1 cubic meter. Hope you can see that's a cubic meter. Or you can say 12.5 times 10 to the negative 3 cubic meter is what it is. All right. And then that finally gives us a value of 3, 4, let's call it, well, it's going to re-round it to 2 significant figures. Yeah, it's 2 significant figures because the KC, so 34, then 34,000 Pascal, so equal to 34 kilopascal. All right, so remember you get the answer in pascals if you work with those units. So, and then I take it to kilopascal. The question does not specify what units of pressure. So yeah, we can leave it in kilopascal. If you want to take it to atmosphere, that's what, 0.34 atmosphere. Relatively, it's the same amount of bar, approximately about 0.34 bar if you did it in bar. I just like to work with SI units, so kilopascal. All right. So this is rounded, so just so you check. So you probably got 31,000 something, and then or 34,000 and something, 34,100 and something, which then rounds to 2 significant figures of 34,000. All right. So that is the total pressure in the flask, is 34 kilopascal after equilibrium has been reached. And it makes sense, you have 3 gases all in equilibria with each other, and how you can use it. And hopefully you reminded yourself that yes, so these are all gases, so even though we work with them as concentration, they should still have a pressure associated with them. All right. Cool. Thank you for watching, and I'll see you in the next video.